Welcome to the deep dive. Today we're tackling statistics.
Hmm.
It really is the backbone for understanding, all the data that's just constantly swirling around us.
It really is.
Our goal today is basically to cut through some of that complexity, see why it's so important. We've looked at sources covering, well, everything from why it matters, the methods, different kinds of data, the whole picture.
Exactly. And in this data-drenched world we live in, getting a handle on statistics isn't just like a nice to have. It's pretty essential for making sense of things.
Okay, so what's driving this huge need for statistical understanding right now?
Well, our sources point to this sort of meteoric growth, really pushed by three big things happening.
Okay, let's break those down. First up, just the sheer flood of data, right?
Oh, absolutely.
Every click, every social media post, sensors everywhere. It's staggering. The sources mention examples like Walmart processing over 1 million transactions an hour,
Wow.
and Facebook, something like 250 million picture uploads every day.
It's mind-boggling. And that's big data, isn't it? It's not just the volume, the amount.
Right, it's also the speed it comes at us, the velocity, and it's all different types of variety.
Plus, what value you can get from it and whether you can trust it. Value and veracity. You need stats to even start sorting through that.
You really do. So, mountains of data. What's the second driver?
Well, you can't handle that data without massive computing power. That's the second piece.
Ah, okay.
We've seen these incredible leaps in processing power. We can analyze data sets now, huge ones, with a speed and, well, sophistication that was just science fiction not too long ago.
And faster algorithms, better ways to see the data, visualization tools.
Exactly. Turning raw numbers into actual business intelligence, driving things like AI, artificial intelligence, teaching computers to learn from all this data.
Okay, data, power.
Yeah.
What's number 3?
Storage. You need somewhere to put it all.
Right. You can't analyze what you can't keep.
Precisely. So huge improvements in data storage capacity, plus things like parallel processing and cloud computing. They let us tackle these enormous problems way faster.
So the data's there, the tools to crunch it are there, the space to store it is there. How do we actually use statistics to pull out something useful?
Yeah, good question. That's where the specific statistical methods come in. One big one is classification.
Okay, what's that?
Think about segmenting your customers, maybe into groups like long-term, loyal ones, medium-term, maybe brand switchers, or just buyers versus non-buyers.
So sorting them out to understand their behavior better.
Exactly. Helps you position products, target marketing, that kind of thing.
Makes sense. What else?
Pattern recognition. This often involves looking at data visually.
Like charts and graphs.
Histograms, for example, can show you income distribution. Is it symmetrical or skewed? Box plots are great for spotting outliers, unusual values, and seeing the spread.
And scatter plots. I've seen those.
Right, they can show relationships, like between age and how much people spend.
Yeah.
Visuals often reveal patterns hidden in just the raw numbers.
Okay, so seeing the shapes in the data, then there's association.
Yeah, that's about finding links between items. The classic supermarket example, market basket analysis.
Ah, like finding out people who buy coffee also tend to buy bread maybe 40% of the time.
Precisely. And that insight helps with store layout, cross-selling promotions.
Gotcha. Coffee next to the pastries, right.
Often, yeah. Then we get into predictive modeling.
This sounds like forecasting the future.
Sort of, using data to predict outcomes. Regression is a common one, maybe predicting expenditure based on income, age, gender.
Okay.
But there are more advanced models, too, like logistic regression or neural networks, which can get quite sophisticated in classifying, say, buyers versus non-buyers, or predicting who might default on a loan.
So using past data to make educated guesses about what's next.
That's the core idea. Now, if we zoom out a bit, all these methods fall under the big umbrella of statistics.
How is statistics itself actually defined?
Well, a classic definition by Ewell and Kendall talks about methods specially adopted to the elucidation of quantitative data affected to a marked extent by the multiplicity of causes.
Okay, that's a mouthful. Quantitative data. Multiple causes.
Yeah, basically methods for understanding numbers influenced by lots of factors. It's interesting to compare that to a more modern term like business analytics. Thomas Davenport defined that as the broad use of data and quantitative analysis for decision-making within organizations.
Sounds quite similar in focused data analysis making decisions.
Very much so. Now, within statistics itself, there are two main branches our sources highlight.
Which are?
Descriptive and inferential statistics.
Okay, what's the difference?
Descriptive statistics is all about summarizing and presenting the data you have, Graphs, charts, tables, calculating averages, just describing what's there.
Making it easy to understand at a glance.
Exactly. Inferential statistics, though, tries to go further. It uses data from a smaller group, a sample, to draw conclusions about a much larger group, the population.
Ah, okay. Like polling a few people to understand national opinion.
That's a classic example.
Yeah.
So the population is the whole universe of possibilities, say, all visitors to your website. A parameter is a numerical value for that population,
Right.
like the actual average time everyone spends on the site.
Which you might not be able to measure directly.
Right, so you take a sample. Sample may be visitors on one specific Tuesday. The average time they spent is a statistic.
And you use that sample statistic to infer or estimate the population parameter.
You got it. That's inference.
Okay, that distinction is clear. Where does all this data actually originate? Primary versus secondary sources.
Mm-hmm. Primary data is stuff you collect yourself for your specific purpose. Surveys you run, experiments you conduct.
So it fits your needs exactly.
Generally, yes. And it's up to date. Secondary data is data someone else already collected, maybe for a different reason.
Like,
Oh, government agencies publish tons of data. Academic research studies, industry reports, stuff scraped from the web or social media. Lots of sources. It's quicker to get, but might not be a perfect fit.
got it. And the data itself, it comes in different flavors, right? Qualitative and quantitative?
Correct. Qualitative data is non-numeric. It describes qualities or categories.
Like gender, religion, maybe favorite brand.
Yep. Quantitative data is numeric, things you can measure or count. Bank balance, family size, temperature.
And quantitative can be split further.
It can, into discrete and continuous. Discrete data can only take certain separate values, usually counts, like the number of cars someone owns or hotel rooms. You can't have 2.5 rooms.
Right, there are gaps between the possible values.
Mhm. Continuous data, on the other hand, can take any value within a given range. Think height, weight, time, or like production quantity measured in kilograms. It could be 10.5 kilograms or 10.57 kilograms.
Theoretically infinitely divisible.
Okay.
Our sources also mention different data set types briefly, like tables, networks, ordered data like video.
Yeah, data can be structured in various ways depending on what it represents. But fundamentally, data sets are made of data objects.
Objects, like what?
The entities being described.
Yeah.
Customers, patients, products, students, whatever you're studying.
And these objects have characteristics.
Exactly. Those are called attributes, sometimes called dimensions, features, variables. Lots of names. Think customer ID, name, address for a customer object.
And these attributes themselves have types. This is getting layered.
Huh, it is a bit, but it's logical. Attribute types help determine what kind of analysis you can do. There's nominal,
No.
categories with no inherent order, hair color, marital status, ID numbers, just labels.
Okay.
Then binary attributes, just two states like 0 or 1, yes or no. Sometimes symmetric, like gender, male, female. Sometimes asymmetric, like a medical test, positive, negative, where one outcome, often coded as 1, is usually more important.
Right. Positive test result matters more.
Then ordinal attributes.
Hmm.
These do have a meaningful order or rank, but the difference between the values isn't necessarily equal or no.
Like sizes small, medium, large. Or grades A, B, C.
Perfect examples. You know large is bigger than medium, but not how much bigger in a consistent unit.
Got it. And finally, numeric attributes. The quantitative ones.
Right. These break down further too, based on whether 0 means nothing. First is interval scaled.
Interval.
These have order, and the differences between values are meaningful and equal. Think temperature in Celsius or Fahrenheit. The difference between 10 degrees and 20 degrees is the same as between 20 degrees and 30 degrees. But 0 degrees doesn't mean no temperature.
Ah, okay. 0 is just another point on the scale. Calendar dates, too.
Good one, yes. Then there's ratio scaled.
How's that different?
These have all the properties of interval data plus a true, meaningful 0 point. 0 means the complete absence of the thing being measured.
Like height. 0 height means no height.
Exactly. Or length, counts, monetary amounts like income or balance. Here, ratios make sense. Someone earning $100 K earns twice as much as someone earning $50. You can't say 20 degrees is twice as hot as 10 degrees C.
That makes sense. Kelvin temperature would be ratio, though, because 0 Kelvin is absolute 0.
Precisely. You've nailed it.
Wow, okay. That's a fantastic run-through of the real fundamentals. We've covered why statistics is just so vital now, looked at key methods like classification and prediction, the difference between describing data and inferring from it.
And the different types of data, where it comes from, and even how data sets are built from objects and these different attribute types.
It really lays the groundwork. It shows how stats gives us the essential toolkit for navigating this, well, data-driven reality we're in.
Couldn't have said it better. It's the language of data.
So thinking about all this, the sheer volume of data, these powerful tools, what are some maybe unexpected areas, things we haven't even considered yet, where you think statistical analysis could lead to really significant breakthroughs or insights down the road? Something for you all to chew on. Thanks for joining us on this deep dive.